Welcome to this problem walkthrough. Today, we'll be tackling problem number 1522, diameter of N-Ary tree. In this problem, we'll explore how to calculate the diameter of an N-Ary tree, leveraging different approaches to solve it efficiently. Let's dive in and solve this step by step. In this problem, we are working with an N-Ary tree, which is a type of tree where each node can have up to n children. The goal is to calculate the diameter of such a tree. The diameter is defined as the length of the longest path between any two nodes in the tree, and this length is measured by the number of edges along that path. To solve this, you'll write a function that takes the root of the N-Ary tree as input. Each node in the tree is represented by a structure containing two fields, a val field, which holds the integer value of the node, and a children field, which is a list of the node's child nodes. The function should return an integer representing the diameter of the tree. Let's look at an example to understand this better. In the input, the root node has a value of 1 and several child nodes with values 2, 3, 4, and 5. Node 2 has two children, 6 and 7, and node 3 has one child, 8. Similarly, node 4 has children 9 and 10. Additionally, node 6 has a child 11, and node 7 has a child 12. The longest path in this tree starts from node 11, traverses up through node 6, 2, 1, and then down to node 3 and its child 8. This path has a total of 7 edges. Therefore, the diameter of the tree in this case is 7. The explanation for this example emphasizes the calculation of the diameter. The longest path we identified, which spans from node 11 to node 8, passes through 7 edges. Thus, the output is 7. Now, let's examine another example to further illustrate how the diameter is determined. Here, the root node has a value of 1 and 2 child nodes, 2 and 3. Node 2 has 3 children, 4, 5, and 6. Additionally, node 4 has a child, 7. The longest path in this tree goes from node 7 to node 3 via nodes 4, 2, and 1. This path traverses 5 edges, so the diameter of this tree is 5. In this second example, the longest path we identified, from node 7 to node 3, consists of 5 edges. Hence, the output is 5. Now consider a simpler scenario where the tree consists of only one node with a value of 1. This node has no children. Since there are no edges in the tree, the longest path is essentially non-existent, and the diameter of the tree is 0. This demonstrates that when a tree has only one node, the diameter is always 0, as there are no connections to measure. Finally, let's review the constraints and edge cases for this problem. The tree can have up to 10,000 nodes, and each node has a unique value. The tree is always rooted, meaning there is a designated starting node, and it is connected, so there are no isolated nodes. Some critical edge cases to consider include a tree with only one node, where the diameter is 0, a tree where all nodes form a straight line, resulting in a diameter equal to the number of nodes minus 1, and a tree with wide branching but shallow depth, where the diameter depends on the longest path. These scenarios highlight the importance of handling different tree structures when solving the problem. To solve the problem of finding the diameter of an N-Ary tree, one straightforward approach is the brute force method. The idea here is to calculate the longest path between every pair of nodes in the tree. To do this, we would perform a depth-first search, or DFS, starting from each node, computing the distance to every other node in the tree, and tracking the maximum distance encountered. Finally, the largest distance found during these computations would represent the diameter of the tree. However, this approach is highly inefficient. Since each DFS traversal takes n time, and we repeat this process for all n nodes, the time complexity becomes n squared, making it impractical for large trees. Additionally, while the space complexity is h, where h is the height of the tree, the real drawback lies in the redundant exploration of overlapping subproblems. This inefficiency makes the brute force approach unsuitable for real-world applications with large datasets. A more efficient solution is the optimized approach, which uses a single DFS combined with post-order traversal. The main insight here is that the diameter of an N-Ary tree can be determined by considering the two longest paths originating from any given node, rather than computing distances between all pairs of nodes. Specifically, the diameter of the tree can be calculated as the sum of the two largest heights among the children of a node. To implement this, we use a post-order traversal, which allows us to calculate the height of the tree in a bottom-up manner while simultaneously tracking the diameter. During the traversal, for each node, we calculate the heights of its children, identify the two largest heights, and update the global diameter accordingly. By the end of the traversal, we return this global diameter as the result. The optimized approach is highly efficient in terms of complexity. With a time complexity of O(n), we only visit each node once during the DFS traversal. The space complexity is O(h), where h is the height of the tree, due to the recursion stack used during the traversal. This method has several advantages. First, it avoids redundant computations by leveraging the tree's structure, making it significantly faster than the brute force approach. Second, it scales well for large trees, ensuring that the solution is both practical and performant. These benefits make the optimized approach ideal for solving this problem, especially when working with trees containing a large number of nodes. The optimized approach was chosen as our strategy because it is computationally efficient and eliminates redundant calculations. By leveraging post-order traversal, we can compute the diameter of the tree in a single pass, making the solution both elegant and scalable. The brute force approach, while easier to conceptualize, is infeasible for large trees due to its quadratic time complexity. The key realization that led to the optimized solution was understanding that the diameter can be determined locally at each node by considering the two largest heights among its children. This insight significantly reduces computational overhead, as it avoids the need to explore all node pairs. While the optimized approach requires slightly more implementation effort, its linear time complexity and minimal space requirements make it the clear winner. It strikes the perfect balance between efficiency and simplicity, making it the best choice for solving this problem effectively. The diameter of an N-Ary tree is defined as the longest path between any two nodes. This path can cross through the root or be entirely contained within a subtree. To solve this, we use an optimized two-pass depth-first search, or DFS, approach. The key insight is that we don't need to compute the distances between all pairs of nodes, which would be inefficient. Instead, we can leverage the tree's structure. By starting a DFS from any arbitrary node, we can identify the farthest node from it, which we'll call node A. Then, a second DFS starting from node A gives us the tree's diameter. This works because the farthest node from A will always lie on the diameter of the tree. The input is provided as an adjacency list, which is a common and efficient way to represent trees for traversal algorithms. Our goal is to implement this two-pass DFS approach to compute the diameter efficiently. To break this algorithm into concrete steps, we start by parsing the input, which is the adjacency list representation of the tree. This allows us to efficiently access the neighbors of any node during traversal. In the first DFS, we begin from an arbitrary node, such as node 0. We use a visited set to ensure that we don't revisit nodes, which could lead to cycles or redundant computations. As we traverse, we track the farthest node we can reach, which we label as node A, and its distance. Once we've identified node A, we initiate a second DFS, this time starting from A. Again, we use the visited set to avoid revisiting nodes. During this traversal, we record the farthest distance we can reach. This distance represents the tree's diameter. This two-pass DFS approach is both efficient and elegant, taking advantage of the fact that we only need to explore each node twice. With this method, we avoid the inefficiency of a brute force approach, which would require computing distances between all pairs of nodes. By focusing on tree properties like the uniqueness of paths and the relationship between farthest nodes, we reduce the problem to a linear time complexity. For additional context, let's consider edge cases and the data structures we'll use. Trees have unique properties, such as having exactly one path between any two nodes, which simplifies the traversal logic. For instance, in a single-node tree, the diameter is 0 since there are no edges. In a linear tree, where nodes form a straight line, the diameter equals the number of edges. For balanced N-Ary trees, the diameter depends on the depth of the tree and its branching factor. To efficiently represent the input, we use an adjacency list, where each node points to its neighbors. This structure allows constant time access during traversal. We also maintain a visited set, which prevents revisiting nodes and ensures we only process each node once. Now, let's apply this algorithm to an example. Imagine we're given a tree with 6 nodes and edges defined as 0, 1, 0, 2, 1, 3, 1, 4, 4, 5. First, we build the adjacency list representation of the tree. For example, node 0 connects to nodes 1 and 2, node 1 connects to nodes 0, 3, and 4, and so on. This adjacency list will be the foundation for our DFS traversal. With the adjacency list built, we proceed to the first DFS. Starting from node 0, we explore the tree and find that the farthest node is node 5, with a distance of 3. This means the path from node 0 to node 5 spans 3 edges. Next, we start the second DFS from node 5. This time, we discover that the farthest node from node 5 is node 2, with a distance of 4. This distance of 4 represents the diameter of the tree, as it's the longest path between any two nodes. Analyzing the complexity of this approach, the time complexity is O(n), where n is the number of nodes. Each DFS visits all nodes exactly once, making the process highly efficient. The space complexity is also O(n), accounting for the adjacency list and the recursion stack used during DFS. This ensures that the algorithm is scalable to large trees. The two-pass DFS approach strikes a balance between simplicity and efficiency, making it a robust solution for this problem. Finally, let's look at the code implementation. We start by defining a DFS function that takes a node and a visited set as inputs. For each node, we iterate through its neighbors in the adjacency list. If a neighbor hasn't been visited, we recursively call DFS on it. During each call, we calculate the maximum distance and track the farthest node. To build the adjacency list, we use a defaultIct, where each node is a key, and its neighbors are stored in a list. Once the adjacency list is ready, we perform the first DFS starting from node 0 to find the farthest node, A. Then, we perform the second DFS from node A to compute the diameter of the tree. The result of this second DFS is returned as the tree's diameter. For example, given the edges 0, 1, 0, 2, 1, 3, 1, 4, 4, 5, the function outputs a diameter of 4, which matches our earlier analysis. This implementation is concise, efficient, and demonstrates how the two-pass DFS approach leverages tree properties to solve the problem in linear time. This Python implementation calculates the diameter of an N-Ary tree using a depth-first search (DFS) approach. The diameter is defined as the longest path between any two nodes in the tree. The function diameter begins by initializing a class-level variable self.diameter to 0. This variable is used to keep track of the maximum diameter encountered during the DFS traversal. Inside the helper function DFS, the algorithm recursively traverses the tree. If a node has no children, it signifies a leaf node, and the function returns a height of 0 for that node. For nodes with children, the algorithm maintains two variables, max1 and max2, to store the two largest heights among the node's children. As it iterates over each child, it calculates the child's height using the recursive DFS call. If the child's height is greater than max1, it updates both max1 and max2. If the child's height is greater than max2 but less than max1, it updates only max2. The diameter is updated at each node by comparing the current value of self.diameter with the sum of max1 and max2, the longest path that passes through the current node. Finally, the function returns the height of the current node, which is max1 plus 1, the height of the tallest subtree plus the current node itself. After the DFS traversal is complete, the maximum diameter is stored in self.diameter, and the function returns it as the result. This ensures that the solution efficiently computes the longest path in the tree, with a time complexity of O(n), where n is the number of nodes in the tree. Here, we start by defining the structure of a node in an N-Ary tree. Each node has a value, represented by the val field, and a list of children, which is a collection of other nodes. We also define three constructors, a default constructor, one that initializes a node with a value, and another that initializes it with both a value and a list of children. Next, we move on to the solution class, where we declare a private variable called diameter to keep track of the maximum diameter of the tree. The diameter of an N-Ary tree is defined as the length of the longest path between any two nodes in the tree. The diameter method serves as an entry point. It initializes the diameter to 0, calls the helper method DFS with the root node, and finally returns the computed diameter. The DFS method is a private helper function that performs a depth-first traversal of the tree. Its goal is to calculate the height of each subtree while updating the diameter. If the current node is null, has no children, or its children list is empty, we return a height of 0 since there's no tree below it. We then initialize two variables, max1 and max2, to store the two greatest heights among the children of the current node. As we iterate through each child, we calculate its height by recursively calling DFS. If this height is greater than max1, we update max2 to hold the previous value of max1 and assign the new height to max1. If it's not greater than max1 but still greater than max2, we update max2 accordingly. Once the loop finishes, we calculate the potential diameter passing through the current node as the sum of max1 and max2, and we update the global diameter if this value is greater. Finally, we return to max1 plus 1, representing the height of the current subtree. We begin with a simple tree that has one root and two children. The tree structure is straightforward, with node 1 as the root and nodes 2 and 3 as its children. Starting at the root node, we initialize the diameter to 0. When we call the depth-first search, or DFS, function on node 1, we note that it has two children. To calculate the longest path through node 1, we keep track of the two largest heights among its children using variables max1 and max2, both initialized to 0. First, we explore child node 2. Since node 2 has no children, its height is 0, and we return this value. Back at node 1, we update max1 to 0, which is the height of node 2. Next, we explore child node 3. Similarly, node 3 has no children, so its height is also 0, and we return this value. Back at node 1, we update max2 to 0, which is the height of node 3. At this point, we calculate the diameter at node 1 as the sum of max1 and max2, which is 0 plus 0, giving a diameter of 0. Finally, we return the height of node 1 as max1 plus 1, which is 1. This completes the calculation for this simple example. The final diameter for the first example is 0, as there are no paths with more than one edge. Now, let's analyze a tree with multiple levels to understand how the diameter evolves with a more complex structure. In this tree, node 1 is the root, with 3 children, nodes 2, 3, and 4, node 3 itself has a child, node 5. Starting at the root, the diameter is again initialized to 0. When we call DFS on node 1, we initialize max1 and max2 to 0 to track the two largest heights among its children. First, we explore child node 2. Since node 2 has no children, its height is 0, and we return this value. Back at node 1, max1 is updated to 0, which is the height of node 2. Next, we explore child node 3. Node 3 has one child, node 5, so we need to calculate the height of node 5 first. Node 5 has no children, so its height is 0, and we return this value. Back at node 3, we update max1 to 0, which is the height of node 5. At this point, we calculate the diameter at node 3 as max1 plus max2, which is 0 plus 0, resulting in a diameter of 0. The height of node 3 is then calculated as max1 plus 1, which is 1, and this value is returned. Back at node 1, max2 is updated to 1, which is the height of node 3. Afterward, we explore child node 4. Since node 4 has no children, its height is 0, and we return this value. Back at node 1, max2 remains 1, as the height of node 4 does not exceed that of node 3. At node 1, the diameter is updated as the sum of max1 and max2, which is 0 plus 1, resulting in a diameter of 1. Finally, we calculate the height of node 1 as max1 plus 1, which is 2. The calculation for this example concludes with a final diameter of 1. In the third example, we analyze a tree with the maximum diameter among the cases presented. The root node, 1, has 3 children, nodes 2, 3, and 4, node 2 has 2 children, nodes 5 and 6, while node 4 has 1 child, node 7. As before, we start at the root and initialize the diameter to 0. When we call DFS on node 1, max1 and max2 are set to 0. We first explore child node 2, which has 2 children, nodes 5 and 6. To compute the height of node 2, we calculate the heights of its children. Node 5 has no children, so its height is 0, and we return this value. Back at node 2, max1 becomes 0, corresponding to the height of node 5. Then, we calculate the height of node 6, which, like node 5, has no children and returns a height of 0. Back at node 2, max2 becomes 0, corresponding to the height of node 6. At node 2, the diameter is updated as the sum of max 1 and max 2, which is 0 plus 0, resulting in a diameter of 0. The height of node 2 is then calculated as max 1 plus 1, which is 1, and this value is returned. Back at node 1, max 1 becomes 1, which is the height of node 2. Next, we explore child node 3. Since node 3 has no children, its height is 0, and we return this value. Back at node 1, max 2 remains 0. Finally, we explore child node 4, which has one child, node 7. To calculate the height of node 4, we first compute the height of node 7. Node 7 has no children, so its height is 0, and we return this value. Back at node 4, max 1 becomes 0, corresponding to the height of node 7. At node 4, the diameter is updated as the sum of max 1 and max 2, which is 0 plus 0, resulting in a diameter of 0. The height of node 4 is then calculated as max 1 plus 1, which is 1, and this value is returned. Back at node 1, max 2 is updated to 1, corresponding to the height of node 4. At node 1, the diameter is updated as the sum of max 1 and max 2, which is 1 plus 1, resulting in a diameter of 2. Finally, the height of node 1 is calculated as max 1 plus 1, which is 2. The final diameter for this example is 2, representing the longest path that spans from node 5 to node 7 through the root. Here, we examine the time complexity of the algorithm, which is O(n), where n represents the number of nodes in the N-Ary tree. The reason behind this lies in the depth-first search traversal. The DFS function is invoked exactly once for each node as the algorithm recursively processes the entire tree. This ensures that every node is visited and its children are handled recursively. Since there are n nodes, we make n recursive calls in total. Additionally, for each node, we iterate through its children to determine the two longest heights, captured as max 1 and max 2. While this might seem computationally expensive, the cumulative number of these iterations across all nodes is equal to the total number of edges in the tree, which is n1. When you combine these factors, the total work performed is proportional to the number of nodes, resulting in a time complexity of O(n). Now, let's discuss the space complexity, which is O(h), where h refers to the height of the tree. This is primarily due to the recursive call stack used during the depth-first search traversal. In the worst-case scenario, where the tree is completely unbalanced, the recursion stack depth will be equal to the height of the tree. This means the space required for the recursion stack would be O(h). Additionally, the algorithm uses a constant amount of extra space for variables like max 1, max 2, and the diameter attribute. Since these variables do not scale with the size of the tree, they contribute only O(1) to the overall space complexity. Therefore, the total space complexity is dominated by the recursion stack, making it O(h). Next, let's break down the best, average, and worst-case scenarios for this algorithm. In the best case, where all nodes have only one child, the tree forms a linear structure. Here, the height of the tree equals the number of nodes, n, resulting in both time complexity and space complexity of O(n). In the average case, for a balanced N-Ary tree, the height of the tree is logarithmic in relation to the number of nodes. This keeps the time complexity at O(n), but the space complexity reduces to O log n, as the recursion stack depth corresponds to the height. Finally, in the worst case, where the tree is completely unbalanced and resembles a linear structure, the height again equals n. Thus, the time complexity remains O(n), and the space complexity reverts to O(n) as well. Now, let's compare this optimized approach with the brute force alternative. A naive method would involve calculating the diameter by considering all possible node pairs, determining the distance between them, and then finding the maximum distance. While this approach works, it requires calculating distances for n*(n1/2 pairs. This leads to a time complexity of O(n squared, which becomes computationally expensive for large trees. Additionally, it uses O(n) space for storing intermediate results. In contrast, the optimized solution we implemented computes the diameter in a single DFS traversal. This drastically reduces the time complexity to O(n), and keeps the space complexity at O(h). This efficiency gain makes the optimized approach far more suitable for large-scale problems. Finally, let's validate the algorithm's efficiency with a mathematical proof of its big O complexity. For the time complexity, each node is visited exactly once during the traversal, and for each node, its children are iterated over. The total number of operations corresponds to the sum of the child counts across all nodes, which equals the total number of edges in the tree, or N1. Adding the n recursive calls to this gives a time complexity of O(n). For the space complexity, the depth of the recursion stack reaches up to the height of the tree, h, in the worst case. This makes the space complexity O(h). Therefore, the algorithm is optimal for computing the diameter of an N-Ary tree, achieving a linear time solution with minimal space overhead. When solving the diameter of an N-Ary tree, there are several common mistakes to watch out for. First, relying on inefficient pairwise traversal to calculate the diameter can lead to O(n²) complexity, which becomes impractical for large trees. This happens because it ignores the tree structure and performs redundant calculations. Another mistake is incorrectly defining the diameter as the sum of the depths of two child nodes of the root. While this might work for some balanced trees, it's not a general rule since the longest path may not pass through the root. A frequent source of confusion is mixing up depth and height. Remember, the depth is the distance from the root, while the height is the longest path from a node to a leaf. Misunderstanding this distinction can lead to incorrect diameter calculations. Finally, neglecting edge cases such as a single-node tree or trees that resemble linked lists can result in runtime errors or wrong outputs. It's critical to explicitly handle these scenarios in your solution. Another pitfall is implementing an unoptimized depth-first search. Without caching results or optimizing recursive calls, you risk performing redundant calculations, which can dramatically increase the time complexity. To excel in interview problems like this, focus on understanding the tree structure. Many tree-based problems rely on leveraging the hierarchical relationship between nodes to minimize redundant computations. For diameter-related questions, post-order traversal is often your best choice, as it processes child nodes before the parent, ensuring you gather all necessary data before moving up the tree. Thinking recursively is also key. Break the problem into smaller subproblems, such as computing the height and diameter of subtrees, and then combine these results. Additionally, recognize key patterns. The diameter of a tree is either the sum of the heights of the two tallest subtrees, if the path passes through the root, or the largest diameter among all subtrees, if the path does not pass through the root. This problem is closely related to several others that you may encounter, especially in the context of binary trees. For example, problem 543, diameter of binary tree, is a simplified version of this problem, focusing on binary trees rather than N-Ary trees. Problem 124, binary tree maximum path sum, shares a similar concept but shifts the focus to finding the path with the maximum sum instead of the longest path. Problem 110, balanced binary tree, involves determining if a tree is height balanced, which requires calculating heights and applying similar traversal strategies. Finally, problem 104, maximum depth of binary tree, lays the foundation for understanding tree height and mastering recursive traversal. Revisiting these related problems can help solidify your understanding of the underlying patterns and techniques. There are also alternative approaches you can consider, each with its own trade-offs. One option is to use an optimized DFS with memoization. By caching the heights of subtrees, you avoid recalculating them multiple times, which significantly improves time efficiency at the cost of slightly increased space complexity. Another approach is iterative DFS using a stack, which eliminates the recursion stack overhead. However, this method can be more complex to implement. Additionally, while breadth-first search, or BFS, is an excellent choice for calculating level information or the tree's height, it's less efficient for diameter calculations due to its inherently different traversal pattern. While BFS may not be ideal for this specific problem, it can be useful for other tree-related metrics. Choosing the right approach depends on the problem's constraints and the trade-offs you're willing to make. Great work! To summarize, we tackled the diameter of N-Ary tree problem, discussed an efficient traversal-based approach, and analyzed its complexity. Remember, mastering tree problems builds a strong foundation for tackling more advanced algorithms. Thanks for joining, and don't forget to like and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!